Greetings. Today we're going to talk about trigonometry. And I'd like to dedicate this video to Olivier Biron, who has been my physics teacher, but we're not going to talk about physics, but mathematics. So as an introduction, I'm going to talk about the course taken in November 2015 about waves. And in waves, you need to compute lots of trig functions and few formulas were presented, and he said that you can either learn these formulas or know how to compute them quickly. And I thought, okay, the proof might involve lots of um, triangles, drawing triangles and stuff like that, and I wasn't very confident with that, and I said, okay, I need to learn that by heart. And I was not willing to do the proof uh, years ago, and um, I thought, okay, I admit that I don't need the proof. And then he said, okay, take the time to do it. And I thought maybe I could do it. And then I started like doing it once. I started doing it twice, three times, and now 4 years later, I think I did it 30 times, not 13, 30. And I was very bottom tier in terms of trigonometry, and now I'm very good at it because, as I said, I'm not good at geometry, but with the method that I will show, I became a pretty good student, and it helped me to fight against sloth, because I don't know why, but it made me interested in doing some proofs, in knowing from where they come in order to better memorize them. So the only thing you need to know is Euler Moivre, and it turned out that I remember these wells well. I had no problem with that, so it's pretty good. It's pretty simple to remember. If you have exponential of a I times a variable, uh, it's equal to the cosinus of that variable, so the real part is cosine, and the imaginary part is sine of that variable. Theta can be in k, so I'm not going to go too much in detail, but it can be a quaternion, can be a complex number or real number. And Euler, that is the expression of cosine and sine. So what matters is the plus and minus. Oops, I forgot I is here. I forgot I, so it's supposed to be over 2i. But I did that document quickly, so sorry, I forgot the I. So it's the base of our knowledge. We always need to remember that to do the proofs. Now we're going to talk about identities, so addition and duplication. What does sine A plus sine B is equal to? So you can draw a bunch of bunch of triangles, but I'm not good at it. And for the product of cosine A times cosine B, who knows? To be honest, I don't know the result by heart. I always do the proof quickly. So we start from Euler Moivre, and we have two ways. Either we can turn into real parts and imaginary part. So here it would be the imaginary part of exponential uh, IA, and here it would be imaginary part of exponential IB. But it turns out that if you do this for this equation, it will not work. And here it doesn't work either because the product of two real parts is not the real part of the product, so it's useless in both formulas. But it's useful for integrals that I will quickly talk about in the end of this presentation, and use the Euler formula to factorize quickly. So we have two equations, so two base equations here, and we will use them to factorize. So um, my reasoning is sine A plus sine B. What can we do about it? Either we can turn it into imaginary parts, but it's not really useful. So this method doesn't work. But it's useful for integrals, as I just said. Okay, so now we talk about Euler. I start with cos A times sine B. So here is my method, so what I write on my documents. So I write 1 over 4i times some products of sum of exponentials, and then I expand the product, and then I factor out. So there are two important things to notice, is to immediately factorize the 1 over 2 of the cosine x and the 1 over 2i. Oops, the I is supposed to be in the bottom of the sine x. So what do I mean by that is on the that formula, when you have a product of cos and sine, you immediately factor the 1 over 2 for the cos and the 1 over 2i in the sine x. So this will be really useful when you need to show those formulas. So immediately I factor out by 1 over 4i, that is the product of 1 over 2 times 1 over 2i. So now what do I do with that? I have the exponential sum. So I have exponential ia, so from the cosine, plus the exponential minus ia, times the same thing for the sine, except that there is a minus. Now I expand the product as a product, as you usually do. And now you can be stuck and not recognize the identity. So usually with those kind of formula, you need to isolate a plus b, or a minus 2 a minus b, or 2a or 2b. And here we can notice that when we'll do the product of ia times ib, and when we will do the product of minus ia minus ib, we'll have those two terms here that resemble a lot, and that will make our sign appear here. Now for the two other products, so exponential ia times minus exponential minus ib, you have the difference that appears. You compute that quickly by organizing them quickly, and you get this formula here by factoring out the minus sign in front and recognizing the sign. So the factorization from this step to this step require Euler, and we're done. We recognize our formula very quickly. And you might answer, oh, it's not very quick, it's pretty slow. When you do that a lot, so not once, not twice, you will start to doing that very quickly. And you're not forced to believe me, but this is actually the way, like, I find it immediately. Well, not immediately because it requires 3 steps, but really fast in terms of computing, because I have the habit of factoring out and I know exactly what I need to do. So yeah, it's an habit, and once again, the more you do that, the more you get involved into the proof, and the more you will remember it. So now, how about the product? So sine A times sine B. We apply the same method. We factorize the 1 over 2a, the 1 over 2i times 1 over 2i. So the I needs to be in the bottom. I made that mistake. Or maybe it's when I converted it to PDF that it did its mistake. So on the bottom you will have I times I. So 1 over minus 2 times 2, so it's equal to minus 1 over 4. And when you do that, you have the exponentials to compute. So you have a product of exponentials. So and what you recognize is again a sum a plus b and a difference a minus b, a minus b. You expand quickly and you refactor out and you get your formula. And once again, here you can recognize the cos, and with the minus 2 in front, it gets the way you intended it to be, so it's correct. I verified those on Wolfram Alpha, so it should not have any mistake. These are just writing mistakes, not really in depth. So yeah, that's correct. Now at home, I recommend you to try to pause the video, to open a worksheet, and to try cos A times cos B. It's exactly the same thing as sin A sin B, and obviously hiding that video. Just factor out the front and compute the exponential part. So you need to be very fast at it. So not watching passively and say, "Oh, I'll do that tomorrow." Okay. And the thing is that you need to have muscle memory on that to compute that really quick. Now I'm going to talk about the baby Euler. So the cases the in which the a and b are equal. So cos square of x is equal to 1 over 4 times the product of exponentials. So I factor out the term in front very quickly. And now we have a product. So the thing to add to our previous reasoning is when you have a product with the same variable, you'll end up often with some 1 appearing and not some sine and some cosine. So how to recognize this is when you'll have the exponential x times exponential minus x that is equal to 1. So this term and this term will be equal to times this term will be equal to 1, and this term times these terms will immediately be equal to 1. So you know that the product of the first times the second and the second times the first is equal to 1 plus 1, so it's equal to 2. And for the other ones, you have exponential ix times exponential ix that is equal to exponential 2ix, and exponential minus ix times exponential minus ix. And you get the formula really quickly. Now, once you reach here, you need to remember that since you have a constant, you can pull this out of the way. Now, sometimes when you have complicated formulas like tangents, sometimes it's not a good idea to factor out the constant term because sometimes it can simplify somewhere else. So when you have when you don't have anything on the bottom, you can always factor out. It works pretty well. So you have 2 over 4, that's equal to 1/2, and then you are left with exponential 2ix plus exponential minus 2ix. You recognize cos of 2x over 2, and you get this formula. Now the same thing applies for sine square, in which you do exactly the same reasoning, and you get the result minus 1 over 2 cos 2x minus 1. Now what about differentiation? So once again, so this is not part anymore of the trig story that I was telling earlier. So this is later in my life. So um, I always had the problem of remembering if it's a plus or a minus when you differentiate or when you integrate the trig functions. So every time I differentiate or integrate a trig function, I do this reasoning. So what's my reasoning? It's in our baby classes, differentiation represents the slope. So here I plotted on Wolfram alpha sine x and cosine x. So sine x that is here has a big slope. It increases near zero. So it's different. Uh, its differentiate. Its derivative must be positive because it increases and nearly equal to one. In fact, it's equal to one because it increases like a linear curve, well, like the identity curve, sorry. And the cosine here is slightly decreasing when you are slightly above zero, but as you get in slightly past the O, it decreases. So it's zero and decreases. Because you can see here it goes downward, so the gradient, so the vector that is the differentiation goes downward, so the derivative is negative, slightly above zero. Obviously we don't consider what happens after it changes concavity, uh, but we just deal with the interval 0 pi over 2 and for sine, and well, for both function 0 pi over 2. And you can get the reasoning the same way for other intervals anyways. So so we have our shape, and that will be helpful to remember the signs. So me, I when I compute the sine x, the derivative of sine x, I don't know. I don't know if it's plus or minus cos, and that's a problem that I have. I know, but I know at least it's some kind of form of cosine x. So is it plus or minus sine? Who knows? I don't really know by heart. I just do this quick reasoning, and I get the sign. So when we replace to something close to zero, so in zero we know that the cosinus of zero is equal to one, because in zero the cos is equal to one, and in the sine the curve increases, and almost like the identity function. So by my rule, since 1 is positive, then it must be a plus sign in front, else it will be minus 1, and then the curve will be decreasing. Therefore, sine x prime is equal to cosine x. Now, I do the same reasoning for cosine. Is it plus or minus sine x? So after 0, near 0, so we're not talking about x is equal to 0, sine x is strictly positive. So cosine x is aiming downward, but not really much, because it's a small variation. It's a I don't want to introduce Taylor expansion in this video, but it's related with Taylor expansion. So we know that sine of 0 is equal to 0, but it's not helpful to know the sign, since we know that at 0 cosine x has a I don't know how that's called, its derivative is equal to 0, so plus or minus 0, it's not really helpful. So we'll consider 0 plus epsilon. So sine of 0 plus epsilon will be strictly positive, obviously not considering the periodicity, the fact that it goes down, just near 0 here. So it's slightly positive, but not really much. And the cosine is going downward, but slightly. This means that uh, there is a negative sign, because since since we have sine x over 0 is positive, then if we want to have a negative derivative, we want to have a minus sign. Therefore, cosine x is equal to minus sine x. Now the same thing, well, not the same thing. We can do the same with antiderivative. So me, what I do is I I compute the derivative of sine x and cosine x, and I remember that it's the opposite of the signs. So when you differentiate sine x and it's plus cosine x, then the integral it's, well, the antiderivative, yeah, antiderivative, it's minus cos x. And when you derivate, differentiate cosine x, you get a minus sine x, and therefore you get plus sine x here, because there is always a change in sign due to the complex number, obviously. You can compute that very quickly. But plus and minus and plus. So that's it. Now, in this year, I have a course in uh, electrical engineering, in which I need to compute often two integrals. I need to prove them every time, and it gets on my nerve. So I thought, okay, let's do a quick maths in order to not lose time over the exam. So I have two integrals, I to be the entire derivative of cosine squared dx, well, cosine x dx, and j to be the antiderivative of cos times sine. So we have two ways. Either we can transform that into with the duplication formula, then do a change of variable. But it doesn't work every time, because sometimes you have very hard trig functions. And now, what do we do with this if we don't want to use the duplication formula? Because when you are in electrical, every time we said, oh, just do the duplication formula. But actually, there is something faster. You recognize that the derivative of cos is sine, and the derivative of sine is cos. So then you do the change of variable, either u is equal to sine or u is equal to cos. It's strictly equivalent, but so you do that change of variable, and then you compute the derivative. So du is equal to sine x dx. So we did the derivative of cosine, that's equal to sine. I missed the sine. Cos prime. Oops. Oops. So yes, so the cosine goes downward, therefore there is a minus sign. Yeah, there is a minus sign, so I forgot the minus sign. There is supposed to be a minus sign here. So du is equal to minus sine x dx, and then you divide by sine x in both sides. Therefore dx, so the dx that we have here, is equal to du over minus sine x, so I forgot the minus sign. And then we can replace it in here. We get the integral of cosine x sine x du over sine x with the minus sign in front is equal to minus cosine x, because the sine x cancel out, and then we are left with cosine x, and cosine x, it's our u. Oops, here it's supposed to be u, because we are in the u world and we did the substitution already. So it's equal to cosine x du, and we know that cosine x is equal to u. So it's the integral of u du. And then it's equal to u squared over 2, and then it's equal to cos squared of x over 2 plus some constant. So now how about the other integral? So cosine squared dx. So I thought about it. So what change of variable can be used? So I thought, okay, maybe use sine x, but obviously if you do that, it doesn't work, because you are left with some kind of uh, integral in which you have uh, the cosine x that is below, so here. So there is not the minus sign in front. Yes, the minus sign is not supposed to be here. So cosine squared of x dx is equal to the integral of cosine x du, because we did the substitution in which we remove cosine x. So we are left with this junk. So now we need to put cos x in the u world, and we are kind of stuck. So we are left with some kind of way to transform it into the u world. So we recognize that cos squared of x plus sine squared of x is equal to 1. Cos x is equal to square root of 1 over 1 minus x squared. And then we can replace it. So we have the integral of square root of 1 minus u squared du. And it's annoying because you are left with that and you don't know what to do. And actually, it's actually the backward step that you have to do. You have to go from this to this integral when you want to solve this, because this is very easier compared to this, because there is a square root and you get a bunch of arcs in, and it's very annoying. So don't compute that, please, and use and do the backward step, and now you're stuck. You reach this step and you can't do it. So there are some integrals in which it's very annoying because you have square roots. However, you need to remember, you need to remember some formula like arcsine prime, arccos prime, arctangent prime, and eventually, you'll have enough knowledge to recognize what the function that you need to integrate is equal to in a trig world. So 1 over 1 plus x squared, you recognize immediately the arctangent. So once again, we are left with a problem in which lots of trig integrals are due to knowledge and practice. So you have to know the basic integrals, you have to do the integrals, you have to recognize the integrals, you have to find a clever change of variable. So these are the methods that are used. Finally, I'm not going to talk too much about the Brioche rules, but I think I did another video on that. So Brioche found some rules for those change of variables in which you have trig functions. So they are known as Brioche rules, Brioche change of variable, trigonometric change of variable, half tangent rule, half tangent change of variable. So if you are interested, you can Google that. Finally, I'm going to talk about series. So the only series you need to remember is exponential x, that's equal to the series of x over n over n factorial. And now you can apply the formulas for hyperbolic geometry. So you can split in cosine, the hyperbolic sine and hyperbolic cosine. So you might say, oh, I'm bad at hyperbolic trigonometry. Don't worry, I'm bad at it too, and it's not a problem. So now you might ask, how do I know the coefficients of cosine h and sine h? So, well, we know that there is the fact that the function in 0. So we know that for cosine h0, it's equal to 0. It's equal to 1, sorry. And for sine h of 0, it's equal to 0. So we know that the first term, in which we have the odd, the even powers, so this one, will have the cos, will be referring to cos h. Now you need to remember that we split with the powers, so since we are splitting between the odd power, the odd power and the even power, then it means that the factorial below will also be the same amount here. So here we have this thingy here that is equal to this thingy here. So always we split, and we split what's on the bottom as well. So now you might say, oh, I don't use very much cosine h and sine h, it's annoying. Now, it turns out that for series, it applies on K, so in C, in complex world. So you can replace x part by I times x. So I times cos I by um, hyperbolic cos of ix is equal to cos x. So you need to remember that formula. It's pretty useful. And you need to remember that sine h of ix is equal to I sine x. So now we are in the new world, and you might say, oh, what do I do with this expression in which I replaced I? Well, it's pretty easy, because I to the power 2n, we know that I squared is equal to minus 1, so we know that I to the power 2n is equal to minus 1 to the power n. Now, for this junk here, you need to recognize that there is a plus 1. So when you factor out the I, you need to factor out one of the I in front of the sum, and you are left with, once again, the since we removed one of the i's, you are left with I to the power 2n, and one I over I to the power 2n is equal to minus 1 to the power n. And there we go. Now, once again, if you apply the real part in both sides, you get this junk is equal to, this junk is equal to this junk. And so you get immediately the Taylor expansion for the cosine, and same goes for the imaginary part of the sine x. Now, in conclusion, so this is what I've learned about trigonometry. Trigonometry and integrals are very knowledge-based, are very practice-based, and I really recommend, if you think you know well about trig, that you are very strong, to actually do the products that I've discussed in this video. And you might say, oh, it's actually interesting because I'm doing it faster. And that's it. And also, when you have proof, be interested into searching where they come from. And don't be passive. Don't be passive when you watch a video. Open a block note when you watch a video. Open a WordPad. Open Paint or any other graphing software in which you draw your ideas on what you see, because you're not passive, you are active and you are interested in. So that's it for this video. I hope you enjoyed it. If you have any question, feel free to ask them in the comments. I'll be glad to answer them. Bye.